This is the third part of the linear regression series. In this video, we will look at mean centering and feature scaling. This video was produced in Korean and translated into English, and my voice was generated by AI text-to-speech. In the last video, we looked at overfitting and regularization and implemented them in code. In this video, we will look at mean centering and feature scaling. Data normalization or standardization is used for feature scaling. And let's learn from Boston's housing price dataset to predict the prices of the test data. Let's use scipy and Scikit-learn libraries and compare the results. Mean centering is a technique that shifts data closer to the origin. Let's look at the example below. We have training and test data like this. Blue dots are training data, and red dots are validation or test data. Shift the training data closer to the origin like this. Then the regression line of the shifted data passes through the origin. This is the regression line, and the intercept of this line is 0. Therefore, there's no need to estimate B, fix B to 0, and just estimate W. The data points follow this model. The epsilons are assumed to be independent, identically distributed, and normally distributed. Taking the average of both sides of this equation, we get the following equation. By assumption, the average of epsilon is 0. Now we subtract the two equations to eliminate B. Then we get this equation. If x minus x bar is called x prime and y minus y bar is called y prime, this equation can be written as follows. The data shifted near the origin are x prime and y prime. If we estimate the regression line for this data, it looks like this. Estimate the parameter W using x prime and y prime data. This W is equal to the slope W of the original data. Now that we have estimated W, we can calculate B from this equation. Then, we can estimate the regression line for the original data. Since B is fixed to 0, W can be estimated more reliably. Normalization or standardization is a technique that not only performs mean centering, but also feature scaling. In multivariate regression, if the xi and xj feature values have significantly different magnitudes, this may also affect the estimates of W and B. If feature x1 has small values and feature x2 has large values, the effects on W1 and W2 will be different. In this case, we need to resize feature values. Normalization is necessary, especially when using regularization. Without normalization, the regularization term may unfairly impose a greater penalty on some coefficients than on others. Let's look at the example on the right. This equation is the third expression on the left. Multiply and divide the first term on the right side by sigma x. Replace x minus x bar over sigma x with x prime. Replace sigma x with w prime. And replace y minus y bar with y prime. Then, the estimation equation for this model can be written as follows. Again, the average of the epsilon is 0. These data points in this figure come from this model. Convert them like this. The converted data are x prime and y prime. The regression line for this data looks like this. W prime is different from W for the original data. Estimate W prime using the normalized data and convert it to the slope of the original data using the formula at the bottom right. Then calculate B using W and the average value of the original data. This is equivalent to the mean centering formula on the left. Mean centering or normalization is applied only to the training data. It does not need to be applied to the validation or test data. Applying mean centering or standardization reduces the time to estimate parameters W and B and provides more stable results. Next, let's use linear regression to train and predict the Boston house price dataset. The dataset has 13 features and 506 data samples. The target value is the house price. The 13 features are like this. The values of feature X1 are very small, and the values of feature X12 are relatively large. Therefore, data standardization is necessary. Let's apply data normalization and ridge regularization. Estimate the parameters W and B of the regression hyperplane using the scipy library. Performance is measured in R². First, read the saved dataset. X is the 13 features and Y is the target price. Split the data into training and test data. Standardize the training data. Calculate the mean of X, the standard deviation of X, and the mean of Y, and standardize the training data using the formula on the right. Write a function to calculate the regularized loss as follows. Here we use standardized training data. Calculate the mean squared error as we did in the previous video, and add the ridge regularization term to it. Also, save the loss history to check whether the losses are being reduced. Now let's perform the optimization process. Set the initial values of the W vector to 0.1. We then use scipy's optimize.minimize function to estimate the optimal W. Since the data are mean-centered, the intercept B is not estimated. Check the results to see if the optimization process was performed successfully. Check if the value of result.success variable is true. If true, the solution has converged successfully. Then, visually observe the loss history saved during the optimization process. Check whether the loss decreases as the iteration progresses. The estimated optimal parameters are contained within this variable. Convert this to the parameters W and the intercept B for the original data. The conversion formulas are as follows. W prime is contained in the result.x variable. B is calculated using this formula. Y bar and X bar are the averages of the training data calculated on the left. And W is the value calculated above. Next, predict the target value of the test data. Apply W and B estimated from the training data, and use this formula to predict Y hat, where X is the test data. Then, visually see the relationship between the actual and predicted Y values of the test data. Finally, we measure the R² of the test data. R² came out to be 0.7602. The loss history is as follows. You can see that the loss gradually decreases as the iteration progresses. The actual Y values of the test data are as follows, and the predicted Y values are as follows. When the actual Y value was 13.1, it was predicted to be 15.5. When it was 33.1, it was predicted to be 32.76. The prediction is not bad. Let's check these results visually. The x-axis is the actual price from the test data, and the y-axis is the predicted price from the training data. If the results are on a perfect straight line like this, when the actual value is 20, the predicted value is also 20, so it is 100% accurate. But our results have this much error. The correlation between the actual price and the predicted price is very high, so the overall prediction can be said to be good. Let's run this code. This time, R² came out to be 0.7665. The optimization process has been completed successfully, and the losses are gradually decreasing. And the results show that the correlation between the actual Y value and the predicted Y value is very high. Next, we will use Scikit's linear regression, ridge, and lasso libraries. It uses the same data as the previous code. First, we use the linear regression library. It applies mean centering internally. Fit the model to the training data and predict the target values for the test data. Visually compare the actual and predicted Y values. Then measure the R² for the test data. Next, let's use the ridge regularization library. The regularization constant is set to 0.01. Fit the model to the training data and measure the R² for the test data. Finally, we use the lasso regularization library. Set the regularization constant to 0.01, fit the model to the training data, and measure the R² for the test data. The actual and predicted Y values of the test data measured on the left are as follows. The results are similar to the previous code, and the respective R² for linear regression, ridge, and lasso models are as follows. In this case, the R² is all measured the same, but it may not be exactly the same. Let's run this code. The result came out like this. The R² for each model was measured like this, and the correlation between the actual Y value and the predicted Y value was measured like this. So far, we have looked at mean centering and feature scaling. And we trained and predicted the Boston house price dataset using scipy and Scikit-learn. In the next video, we will look at total least square, TLS.